Hello students, welcome back. I hope that you are keeping yourself very safe by staying inside home. Also, I expect that you are utilizing the time that is available to you during this situation in a very productive way, so that you will not have any problems of saying I didn't get any time to revise. So the need of the hour now is to judiciously use the time. Please think about it and then try to devote time for studies as well as for your entertainment. There should not be only one thing, right? Anyway, the schedule that you need to prepare should include both. That will be the best schedule that you can make. Now, coming to our topic discussion on electromagnetic induction, students, we have seen in the previous class that magnetic flux is given by, we have seen phi is given by B dot A. This is what we have seen. We have also solved a lot of numericals which were based on this. This can also be expressed as B A cos of angle between the normal vector to the plane and magnetic field lines. Now, we know that when flux changes, EMF is induced, right? Induced EMF is minus of d phi by dt. This means whenever flux changes, EMF is induced. So this gives rise to the fact that what are the factors which can induce EMF? So if you see that change in the flux, any factor which is capable of changing the flux linked with a coil is equally responsible to induce the EMF. So using this concept, what we can say is, if B changes, flux changes, EMF is induced. If A changes, flux changes, EMF is induced. And the third factor which can be there is angle, orientation. If the orientation of the coil changes, flux changes, so EMF is induced. So what we can say, factors affecting induced EMF. So what we can say, all those factors which are capable of changing, first is change in B. This is, if you change magnetic field, there will be a change in flux, hence EMF will be induced. The second factor is change in area linked with the magnetic field lines. Then also an EMF gets induced. And third, change in orientation. What is the meaning of orientation? Angle made by the normal to the plane of coil and magnetic field. These are the factors which are responsible for changing any one of the factor on which flux depends. One of the factor changes, EMF gets induced. That is exactly what we can call as factors affecting. Now, first one, change in the magnetic field. Is it practically possible? Change in magnetic field means that we have to keep on changing the strength of the field. If I take one magnet, then the strength of that magnet is fixed. So B becomes fixed. So normally change in B magnetic field is not taken as a good option for inducing EMF. But change in area and change in orientation can definitely be taken as factors which are in our hand to cause induced EMF. Now see, change in area. Say for example, I am taking this particular thing, that is change in area. How change in area is possible? See here, let us say we have a U-type, see this type of frame, metal frame, and this is a movable conductor. Now in this particular thing, we are placing it in a region where this cross represents the magnetic field. Magnetic field is into the plane of the board. That is what the representation. These are magnetic field. Now let us label this. Say for example, this is P, Q, R, S. This is what we have. Now let us say we give it a velocity V. We are pushing it with a velocity V. Now what we can say is after some time, this QR takes this position. Let us say this is Q dash and this is R dash. So what is the change? What is the change that we observe? See, initial area is area PQRS. This is initial area. What is the final area? Final area is area PQ dash R dash S. Now change in area, this will be final area minus initial area. So when you subtract the final area and initial area, what area will you get? You will get this area. So that is area Q dash R dash R. This is what we get area. How much will be this area? Let us say this side is L. If I say this side is L, so this area will be nothing but PS, which is nothing but QR into RR dash. That is the area. So QR is same as L. What will be RR dash? What we have seen is this particular from QR to RR dash, time taken, let us say it is delta T. So RR dash will be V delta T. This is what we get as change in area. So I will write it as, let us say, delta A. Now delta A by delta T is L into V. This is what we have. Now what we can say is phi, come to this, phi is, see here, normal to the plane of the coil and the magnetic field, they are parallel to each other. So theta is 0 degree. So cos theta will become 1. So what I can say here, phi is BA. So therefore del phi by del T is B del A by del T, because B is not changing. So if you apply product rule, delta B by delta T will become 0. So we get this. Del phi by del T is what? induced EMF? I am talking of magnitude. So magnitude of induced EMF, this is B, and delta A by delta T is what? L into V. So this is the induced EMF, and this is known as motional EMF. Motional EMF. So B into L. Remember this. Why is it called motional EMF? Because the conductor was given motion. So the EMF which is induced is because of the motion in that straight conductor QR. That is why it is called BLV. Now suppose that they are, see here, L and B, they are perpendicular. These are B, na? L is perpendicular, V is also perpendicular, all the three are mutually perpendicular. That is why we got this. Suppose that they are not perpendicular. Suppose that they are not perpendicular. In that case, what is to be done? What we can write is, we can write E is equal to BLV sin alpha, sin beta and sin gamma, this way. And what exactly is that? Alpha is 90 degree. In this case, it is the angle between B and L. Beta is the angle between L and V. Gamma is the angle between B and V. So between all the three quantities, the angles are represented by this. If the three are mutually perpendicular, then we will say it is B into L into V. This is exactly what, this is a very important formula. You will get a lot of numericals based on this. And from the board point of view also, this is important. So we can say, so what do we have? We can say induced EMF E is equal to, we have d phi by dt. So that is also BLV. This is motional EMF. If the three are, all the three are mutually perpendicular. Also, we can write E is equal to BLV sin alpha, sin beta and sin gamma. This is also, we can say, how we can find. So students, see here, please try to understand. We say E is equal to minus d phi by dt, correct? Now flux changes if any one of the term that the flux is made up of, that it is measured, if that changes, then also we will have induced EMF. Now from this we get this, put alpha as 90, beta as 90 and gamma as 90, we will get E is equal to B into L into V. This is exactly how motional EMF, that is change in area. See, there is a change in the area enclosed in the magnetic field, that changes. So this is exactly how you are supposed to proceed for the case of change in area. Now let us take some numericals which are from this particular topic. Well students, let us take one numerical which is based on the concept of motional EMF. See how exactly in this question you will come across the usage of motional EMF. An aircraft with wingspan of 40 meters. So let us record the data. L is equal to 40 meter. This is given. Flies with a speed of 1080 km per hour. So V is given as 1080 km per hour. So let us convert this into, so 1080 into 5 by 18 we will get meter per second. So this will be 300 meter per second. We got V. In eastward direction at constant altitude, where the vertical component of Earth's magnetic field, is given as 2 into 10 power minus 5 Tesla. Find the EMF induced between the tips. Well students, how can we say that there is an EMF induced? So in order to understand this particular concept, please see this. This is the nose of the aeroplane. Okay, This is a wingspan. Earth's field is like this. See here. So L is perpendicular to V. Both of them are perpendicular to B, which means that perfect situation for the application of motional EMF. So what we can say? We know induced EMF E is BLV sin alpha, sin beta and sin gamma. This is what we have. Now here alpha equal to beta equal to gamma, each of them is 90 degrees, just now we saw. So E is equal to BLV. B is how much? 2 into 10 power minus 5. L is 40 and V is 300. So this gives us 24 into 10 power 1, 2, 3 minus 2. So this is same as this many volts we can say. You can write it in millivolts also. So you can say 10 power minus 3. So 240 into 10 power minus 3, so 240 millivolt, or here only we can leave as the answer as 2 into 10 power minus 2 volts. This is exactly 24 into 10 power minus 2 volt is the EMF which is induced. Please understand how exactly B, L and V are related. You will get a lot of questions which are based on this concept. Students, let us take one more question which is based on the concept. The question reads like this: a rod of length L is rotated with an angular velocity omega in a horizontal plane. This means that the coil or the rod is placed in a horizontal plane. The magnetic field B is perpendicular to the plane. Find the EMF induced between its tips. Well, let us visualize this particular question, how exactly it is. First of all, it says magnetic field is perpendicular to the plane. So let us say this is the magnetic field. They represent magnetic field B, perpendicular to the plane. Now it says that a rod is placed of length L. So let us say this is a rod. Whose length is L. It is fixed here. So it is rotating with an angular velocity omega. This is what it is given. Now we have to find induced EMF. Between the tips means this is the point where it is pivoted and this is the other end. Induced EMF. What we can see here is after some time, say t, the instantaneous position of the rod, let us say it reaches this position. Let us say this angle is theta. In some time t, the position after time t, the position is this, that is to say angle moved by the rod is theta. Now this area will be how much? How to find the area? Now area is nothing but area of sector AOB. This area which it has moved is nothing but the area of the sector AOB. And what will be area of sector? It is nothing but pi r square theta by 360 or 2 pi. This is what is area of sector. This is A. So A we get as L square theta by 2. Now change in area dA by dt. dA by dt will be what? L square is constant, 2 is constant, so d theta by dt we get. L is constant, length of the rod is constant. What is changing there? Theta will keep on changing with respect to time, because the rod is this way, it keeps on moving this way. So what will change? Area of that sector is going to change. So we have angle subtended is changing. Now what is d theta by dt? d theta by dt is rate of change of angle. Angular displacement is what? Angular velocity. So we get this as L square by 2 into omega is your dA by dt. We got dA by dt. So what is phi? Phi is B into A. So d phi by dt will be what? B dA by dt. What is d phi by dt? Magnitude of induced EMF. So we can say this is E is equal to B, and dA by dt is L square omega by 2. See, this is exactly how we can find out EMF induced between the tips of this rod when it is rotated in a magnetic field that is perpendicular to the plane of its rotation. So that is exactly how we can find out. This is important. This is a very important derivation. Sometimes numericals directly based on this concept, it is asked in the entrance exams. Now let us go to the next question. Well students, let us take another question which is based on again motional EMF. A disc of radius r is rotated with angular velocity omega in a horizontal plane. So the disc is rotating like this. It is in the horizontal plane, axis will be in the vertical plane, right? Disc is rotating this way with angular velocity omega. The disc is placed in a uniform magnetic field B, which is perpendicular to the plane of the disc. So if we try to visualize this particular question, see how it is. A disc is there. This disc is of radius r. It is placed in a magnetic field. These crosses represent direction of magnetic field which is perpendicular to the plane of the board going inside. That is the direction of magnetic field. And it is rotated with angular velocity omega. See, this is the data which is given. This is how we can visualize the given question in the diagrammatic form. Now the question is, how much is the EMF induced between the axle and the rim of the disc? Axle. Where is the axle? Axle is this. So we will take out this way. See, EMF is taken out this way. We place the connectors here. The disc is continuously rotating. It is touching. They are touching the surfaces. That is exactly how EMF will be taken out from these two ends. Now, how to find out? In order to find out the induced EMF, let us take one small element of the disc. Consider one small element of the disc which is at a distance of x. So what we are doing? Consider a small element of the disk, what should be the features of that element? Length dx, length of the element. Distance, what is this distance? This distance is the distance of the element from the axis of rotation, that is x. Now EMF induced in the element DE, it will be what? BLV. Induced EMF is what? BLV, that we know from the motional EMF. Motion is there, so motional EMF. B is constant, length of the element is dx. What can you say about V? V is the linear velocity. We know V is equal to R omega. What is the relation between linear velocity and angular velocity? V is equal to R omega. Observe, this element is moving in a radius, circle of radius x. So your R will be x. Therefore your V will be what? V is R omega. This is exactly what we get. So write it in the proper form. B omega x dx. This is your EMF induced in that small element. If I want complete total EMF, then total EMF, it will be integration of dE, sum of EMF induced in all the elements. So integration of dE will give us what? B omega is constant, so x dx. Our variable is what? Dx, x, distance. So what will be the limits of integration? Our element can be at the center or can be at the circumference. Therefore the distance will vary from 0 to R. So this is from 0 to R. All the elements we have considered, and summation we are doing, that is net EMF. So what is integration of x? It is x square by 2. So from 0 to R, substitute the limits, upper limit minus lower limit. So therefore induced EMF is what? Half B omega R square. It is same as what we found out in the previous case, where we had half B omega L square. So students, see the approaches of the two questions. How exactly the two questions, although they are giving the same end result, similar end result, but you see the approaches. This is what you have to understand. In the first case, we took area is changing, area of sector, the approach was that we took the area. In the second C, we have taken EMF induced in a small element. See the approach. Please try to understand the approaches which are used to solve the numericals. Don't try to remember the results. Approaches are more important. Clear? Well students, now let us take the next topic. In the next topic, what we are trying to do is, we are trying to establish all the various parameters which are involved with energy, with the EMF induced. See how by considering the energy considerations also we can arrive at the same end result. How? Energy, see, power. We know power is what? We can say F into V. Power is force into velocity, right? That is correct, na? Power is work done by time. Work done is force into displacement by time. Displacement by time is velocity. So we get force into velocity as power. Now force, we can say this force is external force and V we can write. Now if you remember the previous diagram where we considered a U wire frame and we said that the PQ conductor was made to move with a velocity V. How did the conductor start moving? The conductor started moving because of the external force. How much will be the external force? Just to recollect, I am again drawing the diagram. Please try to understand this. It was something like this and we gave a velocity, right? This. So what I can say is this velocity means you are applying an external force. Without external force, how can you make the conductor move? So the external force question arises, how much should be the external force? This external force should be greater than or equal to the force due to the magnetic field on a current carrying conductor. Now in magnetic effects of electric current, you have done how much is the force or acting on a current carrying conductor. See, this is that magnetic force. Now minimum is how much? So minimum F external will be how much? Required is equal to the magnetic force, and that is nothing but BIL. Use this. So this is BIL into V. Now power, this power is what? Electrical power, and electrical power is what? E into I. We say P is V into I. So see, here we have induced EMF into I. Now please see this. What we are getting? See, we are getting the same result that we had in the case of motional EMF. This result we derived from the energy considerations. Also you can work out. This is another route by which we can find. Now coming to F external, what did we write? We wrote F external minimum is equal to BIL, correct? This is what we got. This I think you have done in magnetic effects of electric current. This is the result. Now observe here, I can be written as what? From Ohm's law, E by R. From Ohm's law, V is I into R, I is V by R. So here it is induced EMF. What is induced EMF? E. E is BLV, correct? So what do you get this as? B square L square V by R. This is the external force. This also you can find out. See, this also we can find. We can modify this equation. Another physical term we can extract from this. How? Substitute that F external here. So what you will get? So power P is F external into V. F external is what? B square L square. So what we get this as? B square L square V square by R. See how we can find out different parameters if just we know power is force into velocity. This is exactly how you will get numericals where the power will be asked to compute. You will be asked to find how much is the external force, what is the minimum external force required. Because if the force is not greater than the magnetic force, it will not be able to move in this direction. It will be pulled inside. That is exactly how energy considerations also tell us how to find the various parameters. Well students, let us take one numerical. The numerical read like this: a coil of resistance 400. Let us record the data as we are practicing it. R is given as 400 ohm, is placed in a magnetic field if the magnetic flux phi linked with the coil varies with time, so phi is 50 t square plus 4. The current in the coil at t is 2 seconds. So we have to find current at t is 2 seconds. This is what. Now we know current I will be E by R. This is from Ohm's law. R is known to us. So our aim is to find E. Also, E is what? If I take magnitude of induced EMF, I am not considering the direction. So I will take magnitude as d phi by dt. So this d phi by dt, phi is given. So that is d by dt of 50 t square plus 4. So this gives us how much? This is 100 t. Now at t is equal to 2 second, magnitude of induced EMF is 200 volt. T is 2 seconds. So therefore I will be how much? Therefore I will be E by R, which is 400. So this is 0.5 ampere. So here our answer will be the third choice. That is exactly how we can find out. So students, see here in this question, three things are involved. First, what is involved is we are talking of magnitude. We are talking of magnitude. Second thing, from flux, how to find induced EMF. This is second thing. And third is Ohm's law. See, so don't think that straightforward questions from one formula will be there. Little bit mixing will be there. Now let us take one more question. Well student, one more question. It is a graphical type. In a coil of resistance 10 ohm, so resistance is given as 10 ohm, the induced current developed by changing the magnetic flux through it is shown in the figure as a function of time. See the graph, on y-axis current is plotted, on x-axis time is plotted in seconds. Question is the magnitude of change in flux through the coil in Webers is. Now Q is change in flux by R. We have seen that. We have seen in the induced parameter when we derived the induced parameters in the previous class. We have seen that it is the charge which is independent of time. Induced current and induced EMF both depends on time. This is what we had seen explicitly. So here we have Q is equal to del phi by del R, and this del phi is the magnitude of change in flux. R is given to us. R is 10 ohm. So if you are able to find Q, so what we can say, magnitude of change in flux is Q into R. If you are able to find Q from the graph, we know now what is the induced change in the flux. So how to find Q? Closely observe this graph. It is on y-axis I and x-axis T. If I find area under the graph, that what we will get? Area under the graph is I into T, and I into T is what? Q. That's perfectly right. So Q is nothing but area under the graph. Because area, to find area, we will multiply two perpendicular dimensions. See here, on x-axis T is plotted, on y-axis I is plotted. So I into T if you do, you will get Q, because I is Q by T. or dq by dt or delta q by delta t. So I into delta t will give you delta q or q. So area under the graph. How will you find area under the graph? We see that this figure is triangular, correct? So area of triangle is half base into height 4. So what we get this as? This we get as Coulomb. So now what will be del phi? Therefore change in flux magnitude is Q. It is 0.2 into R is 10. So this is, so our answer is fourth one. So students, see how information, every question is having a small twist. It is not difficult, it is conceptual. So when any graph is given to you, two things you have to think. From the graph, what information can I get? So two informations. One is find the slope of the graph. Second is find the area under the graph. Any one of the two will definitely have some physical significance or meaning. Out here, if I try to find the slope of the graph, then slope of the graph will give me I by t, del I by del t. There is no physical quantity which is represented by delta I by delta t, correct? So slope is of no use to us in this situation. So go for the second thing. Second thing is area under the graph. Now check whether area means multiply the 2, I into 2. Yes, it is giving us some physical quantity with some significance, that is charge, and that is what is required. That is why students, any graph question is given, nothing to get scared. Just try to think of two things. What the slope, does it have any meaning or not? Find area, and possibly you will be able to crack the question with these two informations only. Well students, let us take one more question. This numerical is having b as a function of time. So let us see how to evaluate this. The question reads like this. A circular loop of radius r is placed in a region where magnetic field increases with respect to time as b. So let us write it. B is given as a into t, where a is some numerical constant. Then induced EMF in the coil. Now what we know? We know induced EMF, how do you find? Phi is b into a, na? So induced EMF E, magnitude, I am talking of magnitude, this will be d phi by dt. So phi is b into a. So what we can write? This is b into dA by dt plus a into dB by dt. How did we get this? We have seen this in the previous class also. By using product rule of differentiation, U into V rule, we got this. Now here, what we can say? B is changing, area is not changing, which means that dA by dt will become 0. Why? Area is constant. So differential of a constant is what? 0. So dA by dt will become 0. So we can conclude magnitude of induced EMF is given by A and dB by dt. Now, what type of coil is it? Circular loop. So what will be the area? Pi r square will be the area. And B is given as A into T. So dB by dt will be what? So d by dt of A into T. So what you will get this as? Pi r square A. This is the magnitude of induced EMF. So the answer here is the first choice. See how we can use the concept of induced EMF as well as this particular thing, the aspect that area is constant. We can use this formula to evaluate such numericals.